Now we will talk about delta star connection. Delta star connection, and this is sometimes known as dy connection as well. dy as well. Dy connection, delta y connection, delta and star connection. So that means if we want to draw it, so delta would be, let's say this is as here, and this is a1, this is a2, and this is bs, and this is bs, that source, and this is cs for the source voltage. This is a2, this is b1, this is b2, this is c1, and this is c2. If we draw the phasor for it, let's say this is in this direction, this is in this direction, and this is in this direction. So delta, and the secondary side you have the star one. And let's say this is small a1 and a2, I have a2, b2, and c2 has been used to form the neutral point, and this is b1 here, and this is c1 here, okay, and so the loads are connected at these terminals. So obviously for the user this terminal is only accessible, right? These are connections has been already been made inside the transformer bank in a three-phase transformer, single unit three-phase transformer. Okay, so let's see about the turn ratio. Obviously A:1 is the turn ratio for each phase. Okay, so voltage, the line voltage is here is VAB, VBC. These are the line voltages. Okay, and magnitude of this VAB, if I'll say, that is V at an angle of 30 degree. Okay, V, let's say √3 at an angle 30 degree. VBC √3 at an angle of -90 degree, and VCA is √3V at an angle of +150 degree. So here what would be the phase voltages? Let's say I have drawn it with a small. It would be in capital A1, A2. For primary I am using the capital notation. Okay, so VA1, A2 would be, so VA1, A2 is what? Is the same as that of the line voltage. Okay, so I am writing it. So phase voltage here is same as that of the line voltage, right? So that is, let's say √3V at an angle of 30 degree. Okay, same, they are equal. So what would be the line voltage here at the secondary of the transformer? So to find this line voltage, we need to first find the primary side. We need to find the phase voltage here at the secondary of it. So phase voltage here would be, so what would be VA1, A2? This side voltage, what would be this voltage? So we will compare with this, we will transform the voltage which is appearing across the phase of the primary side. So that is the concept. So we will say, okay, VA1, A2 upon VA1, A2 is 1 by A, right? Because turn ratio for this side we have defined A, primary side is A. Okay, so this VA1, A2 is VA1, A2 upon A. So what would be the line voltage here? VAB. So this is what? This is √3V at an angle 30 degree I am writing upon A. So what would be VAB here? So VAB here would be, so obviously line voltage would be √3 times of the phase voltage here. So √3 of root 3 V upon A, that is the magnitude. And what about angle? So angle, if you will see, so this is the magnitude. What about the angle? So we know in a star connected balanced network, the phase voltage lags the, for a positive sequence, phase voltages lags the line voltage by an angle of 30 degree, right? In a star connected circuit, right, the line voltage leads the phase voltage by an angle of 30 degree, right? So we need to find the line voltage. Phase voltage has been given, phase voltage angle is known to us. So we can directly say VAB would be this quantity and angle would be 30 plus 30, which is 60 degree here. Okay. So if we need to find the ratio of the primary side line voltage upon secondary side line voltage, let's say what would be this ratio? V capital AB upon VAB. So capital AB is root 3 V at an angle of 30 degree upon, so obviously for writing the turn ratio I should not bother about the angle here, root 3 V, and this is 3 V and denominator is A, so A will come here. So this becomes root 3 here. So this is A by root 3. Okay. So you can see here VAB, which is at the primary side, and the secondary side line voltage ratio is 1 upon root 3 of A by 1. Okay. So just the inverse of the previous case. Now that means this transformer, this earlier star delta was used for stepping up the voltage. This delta star is used for stepping down the voltage. So I'll just rewrite it actually to make an important inference out of here. So this is just A by root 3 upon 1. So this is at which side? This is at, the numerator is at delta side, right? And just an inference out of it. And the star side, if you'll see, this is at 1. This is the star side, right? So in denominator side, that is at the delta end, you can see the turn ratio is inherently getting reduced. Okay. So at the transmission level, we use this delta star Y. Okay. So there we started with a generator. Okay. And you just compare this. Just the previous case here. Here the primary side, VL1 primary and VL2 VL of the primary side, line voltage of the primary side and line voltage of the secondary side. So this was what was here. If you see this expression, the primary side was star here, right? Primary side means this side. From star delta, you can energize from either of the side, right? So what I'm saying is, let's say for this, the star side, if you'll see, so this is star side, this is my star side, okay, and the denominator is actually for the delta side. So at the star side, if you'll see, your turn ratio has itself increased, right, by root 3 times than the phase voltages. And in the delta side, if you'll see in this, or other way around, we can say that for the delta side, your turn ratio has reduced. Okay. So in a power system network, generally at the transmission level, what we do is we use a delta star transformer. So if I'm using this delta star, so for the line voltage, if you'll see, I won't be needing, I would be saving one number of turns actually. in stepping up the voltage. If I'm energizing from the delta side, from the star side, I would be actually on the star side, because the line voltage we have seen that the turn ratio is multiplied by root 3 times, right? So this I can say that I would be using this delta star conversion at the stepping up of the voltage, and this star connected transformer is feeding the transmission line, okay, at higher voltage, because this can be easily designed for high voltage side. For high voltage side, it should be the turn ratio should be higher, right? And for low voltage side, the turn ratio should be lower, right? So star side I would be using for the higher voltage side. Similarly here for stepping down, I would be using a star delta transformer to step down this voltage. Now further, this transformer feeds the distribution transformer, and at the distribution level, in the locality level, we want a neutral point and single point as well. So there I would be using again delta star is used, because here we can type the neutral point as well, and here you can give to the loads actually. So this is at distribution level and this is at transmission level. So these are at transmission level, okay, because star side is having inherently a higher turn ratio, right? So for high voltage side, it is easier to use this star side. And here we can have another combinations as well, star star. But this star star we cannot keep the, we'll discuss this as well, we cannot keep the neutral isolated here. Rather we have to ground it. For the very reason we will discuss about it. So even this combination is possible here, but provided you have a neutral connected, the neutral of it is grounded as well. Okay. There are other special type of connections like open delta connection. This is known as VV connection as well. This is only possible in single phase transformer bank, right? That means you are using three unit of single phase transformer to convert into three phase, right? So one advantage in the beginning I said that if this kind of transformer, if there's some fault occurs in, let's say, one transformer or one phase, you can easily remove that transformer and replace it by another one. Let's say meantime you are replacing it, you can still use that transformer as a three-phase transformer but at a reduced power. Let's see how. Okay, so let's say this is transformer A and this is transformer B. This is transformer B, and somehow your third transformer got failed and you have removed it. So now this transformer is not available altogether, C transformer. So can we use this two transformer as a three-phase supply? Let's see. Let's say this is the dot here, this is the dot here, and A:1 is the transformation ratio. A:1 is the transformation ratio. This is only possible when your transformer is a three-phase transformer has been found by using 3 units of single-phase transformer. So let's say this is phase A and you have 3 supplies here, AS, BS, CS. So I have shorted this. This is my capital A2, A1, B1, B2. So dots are here. So obviously this voltage is how much? Let's say I have connected it here. A1 is connected here and B phase is connected here. Okay. So obviously the transformer 1 is having the same line voltage here. What about this transformer 2? So obviously earlier it was connected here, right? So this winding of this transformer B, what is the voltage here? VBC, right? VBC is appearing here. Okay, source as I'm not writing, and here it is VAB, right? Here it is VBC. So what is VAC or VCA? What about VCA? VCA, what is this voltage? So obviously this voltage, if you'll see, if you try to write the loop KVL loop equation here, just see between this loop and this, right? So VCA minus, this is, let's say, increase in voltage, this is also increase in voltage, plus VBC, right, increase in voltage I'm writing positive, plus VAB is equal to 0, and obviously this exists as well, right? So this terminal will actually see VCA is VAB minus of VAB and BC. And in actual three-phase system as well, we know that VCA is this voltage only. So you see that between the line CA, you are also getting this voltage only, which is actual in the actual sense as well. So line voltage is not affected here, okay, for the three-phase supply. Now what about the primary side and secondary side? So at the secondary side also you should receive three voltages, right? The line voltages should not be disturbed. Okay, VAB, VBC and VCA should be same. They should be balanced. So see here, VAB I would write, or here I should write, let's say this is A1. I was using this convention only, so I would be using this only. A2, B1, and this is, let's say, B2. And the dot is here. So obviously the voltage generated would be here only. What would be the voltage generated here? This voltage generated here, VA, let's say I have connected a three-phase load, or just try to see what this voltage is actually. Let's say what is, so here the voltage is VA1, A2. VA1, A2. And what is VA1, A2? This upon VA1, A2, and this is 1 by A. So VA1, A2 is VA1, A2 upon A. And if this is the line voltage, and for line voltage I am generally writing root 3V, okay, at an angle 30 degrees, so this would be at an angle 30 degree upon A. What about VB1, B2? So VB1, B2 is, so this is A, this is B, and this is C. So VB1, B2 would also be root 3V by A, but at an angle of minus 90 degree, as the voltage which is appearing here, which is BC, right? Line voltage VBC. Okay. So this is VA1, A2 is nothing but line voltage VAB. This is nothing but line voltage VBC. So what about VCA? So VCA, if you just try to write it, so VCA would be minus of VAB plus VBC. And this is what desired is, right? If these two are balanced, you have only these two voltages, let's say, you will get VCA as well. So even this VCA is a balanced one. VAB, what is the VAB? Root 3 V by A at an angle 30. Let's say 1 at an angle of 30 plus 1 at an angle of minus 90. And here it is root 3V upon A and minus of it. And if you solve, you see you will get actually root 3V by A, but at an angle of plus 150. So line voltage here and line voltage here, they are all same. Okay, because the line voltage here is the phase voltage here, and the same phase voltage is actually the line voltages here. Now, but see about the power handling capacity here. What would be the power handling capacity? So let's say this connection, I'm using it to power a load. The logic says if you have 3 transformer, power handling or the apparent power of that transformer entire rating was 3 VA or 3S, let's say. If each individual transformer's rating is S, for 3 transformer it should be 3S, right? But we'll see whether this is actually happening or not. Actually the power gets reduced. Let's see how much. What is the power handling capacity of this? Let's say it is connected with a I-star network load, just to make the things analysis a little easier. Otherwise we can do it for the delta as well. So let's see how much power is actually sent to this load. Okay, let's say this is the phase voltage which is appearing at the secondary of it, and this is the current which is coming out of it, IA. Okay, and this is IB here, and this is IC. So obviously the line current here is the phase current which is flowing in this transformer 1. The line current IA is the phase current which is actually flowing through transformer 1. So let's try to draw the phasor for it. Okay, what would be the power consumed by this transformer P1 and A and transformer B? Let's see. Let's say this is the phase voltage here, and this impedance is some angle, Z angle theta. Okay, or Z angle phi per phase. So obviously if I draw the phasor diagram for it, let's say VAN, if it is in this direction, IA would be lagging to it by an angle of phi, right? VAN, this is the neutral point, this is the terminal, VAN into IA. Like IA will lag the VAN voltage by an angle of phi. What about VBN? So VBN would be 120 degree displaced to VAN. Okay, and this would be IB. And what about VC? And VCN would be this, and IC would be somewhere here by an angle of phi here, because the load is also balanced. So what is the power sent by this transformer A? So the power sent by this transformer A, let's say P, that is PA, that would be the voltage appearing across this transformer A, and the conjugate of it, that would be the complex power, you can say, right? So let's say that is VAB, obviously in the vector form, and IA conjugate. So IA conjugate means what is the angle of IA here, and VAB. So if you see in this system, if VAB is at an angle of 30 degree, so we can write the magnitude of it, VAB, and IA is the magnitude of it, and the angle between VAB, that is 30, and angle of IA conjugate, that would be minus phi here, but conjugate will make it phi. So, and if you find the real power, it would be cos of 30 plus phi. Okay, let's say PA, real power, if I say, that would be VAB IA cos of 30 plus phi, PA real, if I say. And what about PB, power consumed by power sent by transformer B? Okay, so you can see here current is coming out of this phase through this side, right? We have assumed IC is in this direction. That's how each phase will have the current inside it, right? So PB is, I would say, in this direction, right? In this direction. So it would be VB instead of it BC, it should be VCB, and IC conjugate. So where it would be VBC? VBC would be leading the phase B by an angle of 30 degree. So if I just redraw it, let's say phi angle is somewhere here, IC here. So this would be, let's say just for simplicity, let's say this is IC here. So if I just extend it in the negative direction, this is this angle, right? VCB. This is VBC. This is VCB. Okay, and if you see this, so angle between these two quantity would be magnitude of VCB into IC, and then angle between these two would be angle of 30 minus 5. Angle between these two quantity would be this. So real power you can consume, you can say that okay, real power and the reactive power component would be there. So let's say we will just try to solve it. PB. So what is PA plus PB? If you will see, that would be, and here the line voltages are same, balanced, so you can actually replace it with the line voltages as well. Okay, so PA plus PB would be, let's say if I just see the real power here, just one calculation, then we can say it for the others as well. So then that would be VA VBC into IC, and then cos of 30 minus 5. Okay, and if you solve it, you will get actually VL. I'm writing for the line voltage, because for both of them, AB and BC, they are the line voltage. So VL, and IA and IC are the line voltages. I am writing IL into cos of 30, 2 times of cos of 30 degree into cos of 5. So, and if you further solve it, you will actually get root 3 VL IL. IL is the line current as well as the phase current for the transformer as well, right? See, this is the phase current for this transformer as well. So I can write it as P here, root 3 VL IL or IP, cos 30 is root 3 by 2, and then cos 5. So if I just focus on the apparent power, that is root 3 VL and IP, or the phase current or the line current. But you think, what would be if I would have used 3 individual transformers? Okay, this was the case when this was the power P, this is for open delta, right? PA plus PB. What would be the power taken by if I would have used 3 like without the faulty condition, all the 3 transformers? So let's say that is P delta. So this P delta would be actually, we can write root 3 VP IP, or we can write 3 times of VP IP, or we can write 3 times of, because phase voltage and line voltages are same, so 3 times of VL and into IP. Here see, I'm not converting the phase current into line current, because in actual delta connected circuit, line current would be different. But here the magnitude of line current and phase current are same here. Let's say for this transformer. Okay, whatever current is flowing in this transformer, in the winding of this transformer, that is the line current as well. Okay, that's why this would be 3 real IP. And if I just find out the ratio of this, P open delta upon P delta, I'm just writing about the apparent power. So then that it would be, I'm not considering the power factor, because this will reflect on the reactive power as well. So root 3 VL into IP upon 3 times of VL into IP. It is actually 1 upon root 3. So in the open delta, actually the power has reduced by 1 upon root 3 times. Okay, so it is not, and if you see this ratio, this will come out to be 0.577. Okay, We were expecting that the power sharing would be 60%, right? 66%, because one transformer we have reduced, but this is not the case. In the open delta connection, we would be operating it at 57% of actually if we would have used the entire 3 transformer as a delta transformer. Okay, so this was the case for open delta connection. So this in some places earlier they were getting 3-phase supply, but using just 2 single phase transformers, and they were getting 3-phase balance supply as well. And this is one advantage is, let's say if I'm using a 3 unit of single phase transformer to make a 3-phase supply and 1 phase goes out, still we can operate it, but at a reduced power. Okay,